Now, believe it or not, there are actually three different types of multiplication that apply to vectors. So we're used to multiplication being only a single operation, but when we deal with vectors, there's actually three different ways of multiplying vectors together. The first type of multiplication is one you've already seen. It's scalar multiplication. You just create a new vector by multiplying an existing vector by a scalar quantity. And what that'll do is it'll change the size of the vector and may also reverse the direction of the vector. We can also determine what's called the scalar product of vectors. So that's when you take two vectors, multiply them together, and your result is a scalar quantity. The notation we use for this I've written here. So this is written as A with a dot between them and then a B. So those are two vectors that are being multiplied to find the scalar product. So we would read that as dot. So the whole thing here would be A dot B. And that's one of the reasons why this type of multiplication is sometimes called the dot product. The third type of multiplication involving vectors is what's called the vector product of vectors. So here you actually multiply two vectors together, but the end result is itself a vector. So the notation we use for that I've written here. It actually appears to be using the traditional multiplication symbol when it comes to two vectors, but we read that symbol as a cross instead of as a times. So we would actually read this whole thing as A cross B. This is why we tend to refer to this type of multiplication with vectors as the cross product. Now, of these three methods of multiplication, we've already seen scalar multiplication. It's scalar product of vectors that we're looking at today. And vector product of vectors actually doesn't fall within our syllabus, so we won't be covering that. Although it is a very useful thing to know, it's not something we're going to be covering as part of standard level mathematics. To write out a general statement of the dot product, we first need to define our two vectors that we're going to be using for the operation. I've just used these general vectors u and v, and you can see I've written their components in general there for x, y, and z. Now this definition, while I'm working right now with vectors in 3 dimensions, it is important to remember that we could use this same definition and everything here that we're going to talk about with the dot product for 2 dimensions as well. We just would make that z component a 0, and then we're working in 2 dimensions again. So if I have vectors u and v, then their scalar product, or u dotted with v, can be found by multiplying the corresponding components and adding them together. So I take the x components, the y components, the z components, I find their products and I sum them. Another way of finding the dot product of two vectors is to multiply the magnitudes of the vectors times cosine of theta, where theta is the angle between them. If you're looking at the rule for the dot product and wondering, where does that come from? Why does it work? Well, I'm happy to provide the proof, but it's in a separate video. So you'll never be required in standard level mathematics to actually reproduce the proof of the dot product, where it comes from. But if you're curious to know why it works and where exactly it originated, I have included that in a separate video that is linked by clicking here. So now let's look at what we can actually do with the dot product. So I'm curious to know, what if the two vectors are perpendicular? What is their dot product at that point? And so we have to think about what this means for a moment. If two vectors are perpendicular, so here is my vector A, and then perpendicular to that will be my vector B. So there's a 90-degree angle between them then. So theta is equal to 90 degrees. So I know from one of my definitions then of the dot product that the dot product of A and B is going to be the product of their magnitudes times cosine of 90. But we should remember from our time doing trigonometry that cosine of 90 degrees is actually 0. And so the product of all those things with 0 is inevitably going to just be 0. So this gives us a very handy rule. If the dot product of two vectors is 0, then I know that those vectors are perpendicular. This gives us a very quick way for checking if two vectors meet at right angles. And you might remember in an earlier video lesson, we were able to figure out two vectors were perpendicular, but we looked at their components and how they were switched around and changes to the sign. Well, finding the dot product is a lot quicker and a lot more effective, less likely to make a mistake, and you can very, very quickly, through a short calculation, verify whether two vectors are perpendicular or not. So what if you have vectors a and b and they're not perpendicular, but instead they're parallel? So here I have vectors a and b. Now because they're going in the same direction, we would actually say that the angle between them is 0 degrees. So again, using that definition of the dot product, I know that the dot product of a and b will be equal to the product of their magnitudes times cosine of 0 degrees. But we should remember again from our time with trigonometry, cosine of 0 degrees is just equal to 1. And so that means that the dot product of two parallel vectors is just going to be the product of their magnitudes. So now we're going to start looking at verifying whether some vectors are perpendicular. So here I have two pairs of vectors. I've got vectors a and b, those are in 2 dimensions, and vectors c and d are in 3 dimensions. And so I know that the dot product of two vectors will be 0 if they are perpendicular. So if I calculate the dot product of vectors, I'll be able to see very easily whether they are perpendicular or not. So for these first sets of vectors, I'm going to calculate the dot product, and what I'm actually going to do is use the version of the dot product where I'm multiplying the components instead. So if I'm ever given components of a vector, that would be the method I use for calculating the dot product, unless I'm actually concerned about what the angle is. So here I'm going to do a dotted with b. That's going to be 2 times 1 plus 1 times -2, which is 0. And so that means that those vectors are, in fact, perpendicular to each other. That shouldn't be too surprising. Those vectors are in 2 dimensions, and you can see how the components are switched, and one of them is changed sign. So I have 2, 1, and then I have 1, -2. And so we mentioned in an earlier video how that was a quick check you can use in 2 dimensions to see that vectors are perpendicular. That line of reasoning doesn't extend as easily to 3 dimensions. You can look at those components. They don't even really match up numerically. And for that matter, there's no discernible pattern whatsoever to see whether they are perpendicular or not. And you might think, okay, well, maybe they're not perpendicular then. Maybe that's the trick. But let's actually follow this through and check with the dot product. So the dot product of C and D is going to be C1 times D1 plus C2 times D2 plus C3 times D3. And so if I multiply corresponding components there, I'll have 3 times 4 for my x components, which is 12. -2 times -1, which is a +2. That's for my y components. And 7 times -2, so that's -14 for my z components. And if I add that up, lo and behold, I get the dot product of those two vectors is equal to 0, which means that C and D are also perpendicular. So again, there was no way to just look at those ones and guess whether they were perpendicular or not. But using the dot product, I was very quickly able to determine that those vectors are in fact perpendicular to one another. So we can then apply the dot product to solving a number of different problems. I have 2 examples listed here. Sometimes you'll be told two vectors are perpendicular. So that's them basically telling you, you know the dot product's equal to 0. And with that information, you might have to solve for an unknown value. So here I'm given the vectors, but one of the parameters, the y component of vector A, is an unknown quantity, represented here by the variable k. And so knowing that the dot product of these vectors is 0, because I'm told they're perpendicular, I can actually establish an equation here using the different components and knowing that that dot product has to be equal to 0, and that's going to let me solve for that value of k very, very quickly. So here I've figured out that k is equal to -6, and all of that was based on my knowledge that the dot product of those two vectors was 0. For the second example, on the right-hand side, I've been given 2 vectors. This time I did it in 2 dimensions. And I know vector A is 2, 1, and vector B is 3, -7, and I want to find the angle between them. So that's actually using both of my dot product definitions. I will need to use, to solve this problem, I'll need to use this equation that involves the components of a vector, but I'll also need to make use of the equation that actually involves the angle, so the one that has the product of the magnitudes and cosine of the angle in between them. So what I'm going to end up doing is actually connecting the information from these together. Now again, for 2 dimensions, we don't worry about the z component, so I'm just going to kind of chop that part off. And so the dot product of these 2 vectors is going to be a1, which is 2, times b1, which is 3, plus a2, which is 1, times b2, which is -7. And so I end up with the dot product being equal to -1. So now to actually connect this to the equation that has the angle in it, I have to realize that I need the magnitudes of both of those vectors if I'm going to solve for an angle. So if I calculate the magnitude of A, it's just equal to root 5, and the magnitude of B is equal to root 58. So if I rearrange my dot product equation here and substitute in those values, I have that cosine of the angle in between them is equal to -1 over root 5 times root 58. And so this now has essentially become a trigonometry question. So I really just have to do cos inverse of both sides and solve for the angle. Now when we're doing trigonometry with vectors, we tend to be working exclusively in degrees. We won't be working in radians. So make sure your calculator is set appropriately. And when I solve for the angle here, I should get 93.4 degrees as the angle between those vectors. Another way we can use the dot product is actually to help us classify shapes. So if I have 3 points here, I know that they form a triangle ABC, and I want to classify the triangle. Now, it's important when classifying a triangle to remember that there's a few different classifications that we use. So we classify triangles two ways. The first way is based on their largest angle. So a triangle can be classified as acute, right, or obtuse. We also classify triangles based on the number of equal sides that they have. And so to that end, a triangle can be classified as equilateral, isosceles, or scalene. So with this in mind, we're actually going to need to check a few different things. We're going to need to check the lengths of the sides of the triangle, and we're also going to need to see if they meet at a right angle or anything like that. So first of all, let's find the vectors between these points. So let's find vectors AB, BC, and AC. So here I've calculated the three vectors. I didn't feel like I needed to show the working for that because this is kind of old hat by now. You should be really comfortable finding vectors between 2 points, especially in 2 dimensions. And so now what's really important is to actually see, are any of these vectors perpendicular? That will allow me to determine whether the triangle in question is an acute triangle, a right triangle, or an obtuse triangle. So let's start by taking the dot product of AB and BC, and we'll go from there. So that would be 4 times -3 plus -3 times -4. So this is -12 plus 12, so that's 0. So that tells me then that angle ABC is 90 degrees, because what it's saying is where AB, so vector AB meets BC, that's where they're perpendicular, so that's where the 90-degree angle is. So I know that I have A, B, C, and this is a right angle. So it's not equilateral, obviously, but we know that it is a right triangle. So now the question is it a right isosceles triangle or a right scalene triangle? And so the way that we would check that is by finding the magnitudes of the different sides. So I will find the magnitude of AB and the magnitude of BC and the magnitude of AC. So here I've calculated the magnitudes of these three vectors. Again, didn't need to show the working for that because you've probably done this a million times by now, but I find that 2 of them have the same magnitude. AB and BC are of length 5, whereas AC is of length root 50. I don't need to know exactly what that is, but I know that root 50 is not 5. So that tells me, because 2 sides match up, I know that it's isosceles. It is definitely not scalene, and definitely not equilateral or obtuse or acute. So we know that this is a right isosceles triangle, and now we've been able to classify it using what we know about the dot product.